A single point cannot have a slope. Through this point, I can draw this line, or this one, or this one. In fact, infinitely many lines pass through exactly the same point. And yet, calculus looks at that point and confidently chooses one number. Not a range, not a guess, one slope. So where did that number come from? By the end of this video, you will see that the derivative is not a rule for moving exponents. It is the number that nearby points are forced to agree on, and the best local prediction a function can make. Slope compares two changes. It asks how much the output changes for a given change in input. On a straight line, as 2 points move together, the ratio of rise to run remains completely unchanged. But bend the line into a curve and that ratio changes depending on which 2 points you choose. Imagine your position is given by s of t equals t squared. At t equals 3, your position is 9 meters. But that one isolated fact says nothing about how fast you are moving. Standing at 3, 9, infinitely many different curves pass through your position. One rising steeply, one nearly flat, one falling, one with a sharp corner. A single coordinate does not contain its own derivative. To know your local behavior, the surrounding function matters. You cannot determine your motion by looking only at yourself. So you ask a neighbor. Choose a second point at t equals 4. The position is 16. The average rate between t equals 3 and t equals 4 is 16 minus 9 over 4 minus 3, which equals 7. The neighbor at t equals 4 reports an average rate of 7. Now move the neighbor closer. At t equals 3.5, the rate is 6.5. At t equals 3.1, it reports 6.1. At t equals 3.01, it reports 6.01. What do you think the next neighbor will report? Your neighbors do not give you the same answer. The distant neighbor says 7, a closer neighbor says 6.5, a much closer neighbor says 6.1, and the neighbor almost touching you says 6.01. Different answers, but not random answers. Look at the lines they leave behind. Listen to the numbers. They are all leaning towards the exact same direction, 6. The number none of your neighbors actually reported exactly, but the number they were all pointing towards. This line is not selected because it merely touches the curve. It is selected because every sufficiently close comparison points towards its slope. What happens if we set the interval h to 0? On the left, plugging in h equals 0 gives 0 over 0. Division by 0 is undefined. On the right, keep h as an ordinary non-zero number. Expanding 3 plus h squared minus 3 squared gives 6h plus h squared. Divide by h to get 6 plus h. As h approaches 0, we are left with 6 plus h. The limit does not ask us to divide by 0. It asks what ordinary calculations approach before the interval reaches 0. 6 is not merely the angle of a green line. It is a prediction rule. If time increases by a tiny amount, position increases by approximately 6 times that amount. Move forward by 2/100ths of a second. The derivative predicts an increase of 6 times 0.02, which is 0.12 meters. 9 becomes approximately 9.12. The exact position is 3.02 squared, which is 9.1204. The tangent line missed by only 4/10,000ths. That is what the derivative really gives us. Not just a slope to draw, but a local model we can use. From far away, the function is curved, but the closer we examine the neighborhood of one smooth point, the more the curve behaves like its tangent line. Zoom in once, twice, 3 times. Inside the viewfinder, the fundamental formula of calculus emerges. F of x plus h is approximately f of x plus f prime of x times h. New output is approximately current height plus slope multiplied by horizontal nudge. The derivative is a slope, But it is not just a slope. It is the agreement reached by infinitely close comparisons. It is the multiplier connecting a tiny input change to its output change. It is the straight line model hiding inside a smooth curve. The derivative is a local prediction rule. And once a derivative predicts tiny changes, what happens when we add all those tiny changes back together?